Hello guys, welcome to our first video in our Precalculus full course series. Our first section here in chapter 1.1 will be real numbers. So you may notice that this is the first big lesson of Algebra 2. It is in our series as well, and this is because real numbers form the foundation of all mathematical reasoning. So in this section, we're classifying real numbers into their proper subsets. Natural numbers, whole, integer, rational, real, plus our irrational real numbers. And then we'll apply the fundamental properties of the real numbers here, which would be commutative, associative, distributive properties to perform operations using properties of negatives and fractions. We'll be locating numbers on the real line, describing sets and intervals using appropriate notation, and computing absolute value and distance. So in other words, every single concept in this section is going to recur throughout the entire Precalculus course. So we're always asking ourselves, what type of number is this? Before classifying, we walk the hierarchy. Here's a little diagram here of our hierarchy. From natural numbers up to real numbers. And we always convert to decimals when we're ordering or comparing any real numbers. For irrational and irrational, we're asking, can you write this as a fraction of two integers? For properties, we're asking which property lets us rearrange, regroup, or distribute here. Then we get into interval notation. So we're asking, is this endpoint included or excluded before we write any bracket or brace? Parentheses, for example. And then for absolute value, we're always connecting to the geometric meaning, so the distance from 0 on the number line. And we'll be just distinguishing carefully between an empty set and a bracketed 0 set. And for fractions, we're looking to use the least common denominator method for addition. So, we're not guessing the common denominator. We want to use the LCD method clearly and intentionally. All right, that's just a real quick little rundown on what we're covering. Let's go ahead and jump straight into our lesson. Let's take a look first here at our visual. So natural numbers are the counting numbers. 1, 2, 3, 4, 5, for example. They do not include 0. Whole numbers are natural numbers plus 0. 0, 1, 2, 3, 4, for example. Integers are all whole numbers and their negatives. So -3, -2, -1, 0, 1, 2, 3, for example. Rational numbers. Any number that can be written as m over n, where m, n are not an element of z, and n does not equal 0. Now, a rule of thumb for rational numbers is that the decimal form will terminate or repeat forever. So, for example, 1/2, -3/7, 46, 0.17, 0.6 with the repeating bar over it. So it goes on forever, 0.66666 on and on forever. Now, irrational numbers are numbers that cannot be written as m divided by n. So decimal form is non-terminating and non-repeating. For example, the square root of 3, the square root of 5, the cubed root of 2, pi, 3 divided by pi squared we have over here. This does not include our perfect squares. For example, the square root of 4 is 2. All right, so every natural number is also a member of which other sets? It's also a whole number, an integer, a rational number, and a real number because the sets are nested, as our visual shows here. Is every integer a natural number? No, negative integers and 0 are integers, but not natural numbers. Now, I will say that students oftentimes confuse whole numbers and natural numbers. So let's remember that whole numbers include 0. Natural numbers begin at 1. Every integer can be written as n divided by 1. So every integer is rational, and therefore no integer can be irrational. All right, so every real number has a decimal representation. The form of that decimal tells us whether the number is rational or irrational. For example, here in our text, we'll go over here to the right slightly. We have a terminating fraction here with 1/2, which becomes, in decimal form, 0.5000, or with the repeater bar over the 0. So this is rational. 2/3. This is a repeating decimal form, does not terminate, goes on and on and on and on forever. This is rational. What about a longer block of repeating? For example, 157 divided by 495, where we have 2 digits here with our repeater bar over it, still rational. Even a much longer repeater, like 9/7, where every digit after our decimal place is repeating, still rational. All right, so these can be written as fractions. That's really what we want to notice with our repeater decimals. For example, 2/3, 157, 4/95, 9/7. What about a square root of a non-perfect square, by the way? Right, because the square root of 4, for example, would be 2. But what about the square root of 2? Notice this is non-terminating and non-repeating. Here's our big decimal. This is irrational. And pi, maybe our most famous irrational number. There we go. Non-terminating, non-repeating as well, so irrational. All right, is 0.333 rational or irrational? It's rational because it's a repeating decimal that's equal to 1/3. What about the square root of 4? Is that rational or irrational? That's rational because the square root of 4 is 2, which is a whole number and therefore rational. So let's remember, not all square roots are irrational. The square roots of perfect squares, 1, 4, 9, 16, 25, 36, down the diagonal on our multiplication chart, creating our perfect squares, are rational. Only square roots of non-perfect squares, for example, the square root of 2, the square root of 3, the square root of 5, and so forth, are irrational. All right, so any repeating decimal is a rational number, and we have a technique here in our margin to convert it to a fraction. Let's zoom in on that. So let's say we want to convert this into a fraction. This is a repeating decimal, so we can convert this into a fraction. So we'll let that be equal to x. And we want to move that over however many places will be one full repeater. So for example, 5 isn't included in the repeater. It ends here for the first. So we'll want to move that over 1, 2, 3 places to the right. In order to do that, we'll need to multiply x by 1,000. So the key here is we're multiplying x by 10 to the whatever length of repeating block power, and then 10 to the non-repeating digits power. So here, for example, our next block will be 10x because we have one non-repeating digit. And then we're using elimination through subtraction to eliminate the repeating part. So we'll set this up as such, and we will subtract. 1000x minus 10x will get us to 990x, and we'll subtract 35.4747 on and on from 3547.4747 and so on. And that's how we get to 990x equals 3512.0. Now we're ready to finish solving this algebraically. We'll get to x equals 3512 over 990. So again, the idea is to multiply x by the appropriate powers of 10 and then subtract to eliminate the repeating part. So one more time, the number of digits in the repeating block determines which power of 10 to use. 1 repeating digit, multiply by 10. 2 repeating digits, multiply by 100. 3 repeating digits, multiply by 1,000, etc. All right, let's go to our next part, properties of real numbers. Here we see we have commutative, associative, and distributive properties on our visual. Let's quickly take a look at that. So for commutative property, when we add two numbers, the order does not matter. For example, 7 plus 3 equals 3 plus 7. Commutative for multiplication, also the same idea applies as it does for addition. When we multiply two numbers, order does not matter. For example, 3 times 5 equals 5 times 3. This is why we can multiply length times width or width times length for area of a square rectangle, and we will arrive at the same number. Now for a square, they would both be the same regardless, right? So maybe I should say just for a rectangle. All right, for our associative properties, we have addition and multiplication as well. For addition, when adding three numbers, the grouping does not matter. For example, 2 plus 4 plus 7 is equal to 2 plus 4 plus 7. And the same thing applies for multiplication. 3 times 7 times 5, 3 times 7 times 5. Order does not matter. Grouping does not matter. And then we have distributive property. So multiplying by a sum gives the same result as multiplying each term and adding. For example, 2 times 3 plus 5 equals 2 times 3 plus 2 times 5. 3 plus 5 times 2 equals 2 times 3 plus 2 times 5. Now, the most important of these that we'll be working with more heavily in precalculus, because we're probably pretty good with commutative and associative properties by now, is the distributive property. This is super important out of the three because it describes how multiplication and addition interact with each other. So we can think of this property as the engine behind all of algebra. So with that being said, let's go straight to the distributive property. Here's a nice little visual. Almost looks like dominoes here. Let's go take a look. We have 2 times 3 plus 5 to show that this is equal to 2 times 3 plus 2 times 5. Now let's work through the next problem carefully up here in our first example. So part A here will be a direct application, and part B requires applying the distributive property twice, actually. Let's start here with A. All right, so we're going to apply that distributive property directly by multiplying 2 into each term inside of our parentheses to get to 2 times x and plus 2 times 3. 2x together, 2 times x is 2x, 2 times 3 is positive 6. That's how we get to 2x plus 6. All right, so step 1 there was to apply the distributive property, and then we simplified in part 2, or step 2. Simple enough. Let's take a look at B. Here we're going to treat the entire quantity, A plus B, as one factor that's multiplying the sum x plus y. So in other words, we're applying the distributive property twice. So let's go through this step by step. The first step, when we distribute A plus B across x plus y, we're going to get to A plus B times x plus y, which gets us to A plus B times x plus A plus B times y. Distributive property. Now the question is, how do we expand A plus B times x? And the answer is we apply the distributive property again. A plus B times x will get us to AX plus BX. And the same for A plus B times y will get us to AY plus BY. Now our associative property of addition will remove the parentheses. And that's how we get to AX plus BX plus AY plus BY. All right, so again, in our final step here, we're going to remove all our parentheses using the associative property of addition, which, by the way, tells us the grouping of addition does not matter. And we want to pay close attention to the justification there. Because in this class, we're learning math on a deeper level, right? We're not just memorizing those steps, but we want to understand the math very well. Super important to understand why the math works to prepare us for Calculus 1. And for my students who are wanting to go into fields that require a lot of math, there's Calculus 1, Calculus 2, Calculus 3. And by the time you're done with Calculus 3, well, you may be ready to take your first Introduction into Quantum Mechanics course by then. But yes, we're at the point of wanting to understand the math on a deeper level and not just memorize the steps. So we will work on justifying every step as we go along the course. All right, let's continue on to part 3, addition and subtraction. This is where we start to look at additive identity, additive inverse, and properties of negatives. So the number 0 is special. Let me zoom in a bit. Adding 0 to any number leaves it unchanged. This is called the additive identity. And every real number, A, has an additive inverse, negative A, such that A plus negative A is equal to 0. Now subtraction is defined in terms of addition. A minus B equals A plus negative B. That's why we say that subtraction is really adding the opposite for a simple definition there. Here's a nice visual for those properties of negatives. Let's quickly go through each one. Property 1. Negative 1 times A equals negative A. So multiplying by negative 1 is the same as taking the negative. Here's our example. Property 2, negative A is equal to positive A, like negative 5 is equal to 5. So the negative of a negative is a positive. Negation of a negation goes back to positive. What about 3? Negative A times B equals A times negative B, which equals negative AB in parentheses there. We can see that played out in our example. Or in other words, a single negative sign in a product makes the product negative. Property 4, negative A times negative B equals positive AB. Here's our example. In other words, two negative signs in a product give a positive result. Okay, our next property, negative A plus B equals negative A minus B. Here's our example. The negative of a sum equals the sum of the negatives, in other words. And our final property, number 6, negative A minus B equals B minus A. Here's our example. And this means that the negative of a difference reverses the order. Pay close attention to number 6 here, that A minus B and B minus A are negatives of each other. Or in other words, A minus B plus B minus A will equal 0. Because this will be super important for absolute value arguments later in the section here. All right, let's go to example number 2. Using properties of negatives. Let's assign our properties here. X, Y, and Z are real numbers. So we begin with A. Which property applies to negative x plus 2 equals negative x minus 2? That's property 5. Negative x plus y minus z equals negative x minus y minus negative z, which gets us down to negative x minus y plus z. Notice our first part here is property 5. Then we move on to property 2. So we want to keep in mind here is that, for example, B here is that negative A does not mean necessarily that it's negative. Whether negative A is negative will depend entirely on the value of A. For example, if A equals 5, then negative A will be negative 5. But if A equals negative 5, then negative A will equal negative 5, which makes 5 positive. And this is a persistent student misconception because it's quite abstract, so we have to train our brains to work with the negative values. Now, practicing these negative properties throughout each problem will train our brain like a muscle memory to accept that a double negative gets us back to positive. All right, that will conclude our first video here. Part 1 of our 1.1 section here of chapter 1. Join us soon and we'll be jumping straight into part 2. Let's move over here where we will be exploring multiplication and division. See you soon. Bye.